Hey guys, we're back with episode 2 of Fun with Physics. We have a good episode today, I guess you could say. We're going to work with quarks. As you might recall from our last episode, we were working with fermions that are called leptons. So we had our neutrinos and our partners for the neutrinos. We have the electron, the muon, and the tau with the negative charge, and then we have our tau neutrino, muon neutrino, and our electron neutrino with a neutral charge. As you might recall also, our fermions, all of our fermions have a half integer spin. Just before I get into our episode today, I just want to talk about some things that I messed up on and some things that weren't quite right. Just real quick, a muon, let me just get into that because there is a muon experiment that is going to be held at Fermilab, and I'm sure I mentioned that last time. And we're looking with our electromagnet particle storage ring. We're looking for its distinct wobble in its electromagnetic fields. Its distinct wobble, and it's just a type of. It's a weird particle. It's a short-lived particle. And it decays in 2.2 microseconds, and it's a really short-lived particle. But what I forgot to mention is that it is 200 times the mass of an electron, and you see that's interesting because a muon, when a muon decays in those 2.2 microseconds, it decays to form 3 new particles. An electron and 2 neutrinos that go undetected in a particle accelerator. So those go undetected. Good thing for the new neutrino project that's being held at Fermilab and in I think Minnesota. I'm not sure. There's a near and far detector. I'll get into that at the end because I'm really interested in neutrinos, and I love the way neutrinos are found, but I'll get to that at the end. And the other thing I wanted to touch on is that last episode I said that the giga electron volt, mega electron volt, and the electron volt was represented a certain way, and I wasn't quite correct on that in that way, so I would like to just clear it up. It's actually represented like this. Let me just get, it's like this pretty much. Where is it? Yeah, it's represented like this, and I'm sure I put something like G/EV. It wasn't quite correct, so I just wanted to show you that. So we do have some, so I just clear some things up there. And now we can get into our quarks, but let me just again state one more thing. A way muons are detected are by high energy, I guess you could say, you can find them a lot in particle accelerators when you're working with muons, obviously. Cosmic ray interactions and high energy interactions, in general. Muons are pretty interesting, like I said. It's weird how they, again, decay into 3 other particles, but again, the reason why is because how massive it is, you know, compared to an electron, which does form when it decays. And again, you know, yeah, and you know, high energy interactions and cosmic ray interactions, like I said, pretty much, that's how you can detect muons. So that's something right there. You know, that's pretty much it, and I want to get into our quarks now. So again, what is a quark? Just like I asked what a lepton was. Well, a quark is the main constituent of all matter. You know, they make up hadrons that are baryons, like protons and neutrons that are found in atomic nuclei. So, you know, we have quarks that are bound together by gluons that make these protons. And again, like I said, they are elementary particles because they don't have a substructure. And that's why they're elementary particles, they're constituents of matter. That's why they make up these protons and neutrons, which are composite particles, the hadrons that are baryons. So, as you know, they make up atomic nuclei. So, that's why they're bound together by gluons, and we'll get to gluons when we study our bosons. And we will go over our theoretical bosons as well, but, you know, really interesting. So we know that they are the main constituents of all matter, and there are different flavors, I guess you could say, that they're called flavors. I say types, different types of quarks. You know, we have an up quark, we have a down quark, we have a charm quark, a strange quark, a top quark, and a bottom quark. Excuse me. And you might ask, well, what quarks make up these protons and neutrons? So the up and down quarks make up protons and neutrons. There are two up quarks in a proton and one down quark in a proton. There are two, just opposite of that, a neutron has two down quarks and one up quark. Again, still main constituent of matter. And we know by research that that up and down quarks are pretty common in our universe, and they are the most common. You know, we only find strange quarks, charm quarks, top quarks, and bottom quarks. You know, we only find the odd quarks, again, the strange top, bottom, charm. We find those quarks in different particle accelerator experiments. Sometimes, you know, we don't always have experiments like that, but yes, we can find one. We can find some of those. Again, most common up and down quarks. And I just want to give you a quick model. I probably should put this at the end, but I want to put this right here. I'm just gonna show you a small. It's a Feynman diagram, and it's about quarks, and you know, this is really interesting. You see, this is what happens is an electron and a positron pair. An electron-positron pair collides and emits a photon, and the photon later becomes a quark and an antiquark pair, with the antiquark emitting a gluon. So this is it right here, just right there. And That's one of my favorite Feynman diagrams. That one is awesome, and so that they're pretty. I love Feynman, Richard Feynman's amazing Feynman diagrams. So now again, our types of quarks. Again, we have the up, down, charm, strange, and top down, or top bottom quark, I should say. And now we can get into the mass, the spin, the electric charge. So for again, all quarks, all fermions have a spin of, have a half spin, as opposed to bosons that have a full integer spin, one integer spin. So they all have that. We can clear that up. The electric charge, an up quark has a 2/3 positive electric charge. Down quark has a third negative electric charge. A charm quark has a 2/3 positive electric charge. A strange quark has a negative 1/3 electric charge. A top quark has a 2/3 positive electric charge, and a bottom quark has a negative 1/3 negative charge. So we now know our spin, and we now know our electric charge. Now to our mass. Our mass is pretty weird for these quarks. They're weird. And for our up quark, we have a 2.4 mega electron volt. For our down quark, we have mega electron volt speed of light squared. Remember that. For our down quark, we have a mega electron volt speed of light squared. For our charm quark, we have a 1.27 giga electron volt to the speed of light squared. We have our strange quark that has a 104 mega electron volt speed of light squared. We have our top quark that has a 171.2 giga electron volt to the speed of light squared. And we have our bottom quark, which is a 4.2 giga electron volt speed of light squared. So now we know our mass, our spin, and our electric charge. So those are the main things really you need to know about quarks. We know that they are the main constituents of all matter. Pretty much the main concept of quarks. And again, just to go by real quick, but we know that the fermions include all of the particles with their assigned antiparticles. So let me just go over those real quick. We have our anti-up quark, anti-down quark, anti-charm quark, anti-strange quark, anti-top quark, anti-bottom quark. So we know that. And again, quarks interest me. They're pretty, they're weird. And the only particle that that's known to experience all four fundamental interactions: electromagnetism, gravitation, strong interaction, and weak interaction. For some reason, I just forgot electromagnetism for some reason. But those are our strong interactions, or those are our four fundamental interactions. And again, those are the things we know about quarks. And so that's about it for our particle physics research here at practice. And our next episode, we will probably be going over bosons, and we have obviously the photon, the W boson, the Z boson, and the gluon. And then we have the graviton, hypothetical yes, but we will get into that. And funny thing about W bosons that we'll get into. But yeah, that's about a wrap for our episode, and I will put the links in the description for amazing experiments that are going on. I mean, just amazing. I forgot to mention, actually, another main thing about quarks. A state of matter that was believed to have formed right after the Big Bang was a quark-gluon plasma. So again, these protons and neutrons are comprised of quarks and the quark-gluon bond. So we have our singularity, and once the Big Bang happened, there was a high energy density, so protons were melted, neutrons were melted, and we had quark-gluon plasma. And that's a really, there's a really interesting experiment that's being held at CERN. It's called ALICE, the Large Hadron Collider. It's called ALICE, and they do experiments about this quark-gluon plasma state of matter that is believed to have formed right after the Big Bang. So quarks are amazing. Physics is amazing. This is an amazing time for science right now. Science and math research. I mean, it's just amazing. And again, this is about it for our episode. I will put links in the description for 3 amazing experiments. ALICE for the quark-gluon plasma. Again, the muon G-2 experiment that is going to be held this year at Fermilab, and then our new neutrino experiment, NOVA, and we're going to be obviously experimenting neutrinos, and we have a near and far detector, one that's I think 4,000 tons and one that's 14,000 tons. And I'm pretty sure the other one's in Minnesota or Michigan, somewhere like that. But it's going to be really interesting. I mean, we need neutrinos. I mean, we need to experiment with neutrinos because we need to know why the universe is made of so much matter and not antimatter. And 3 ways that neutrinos are created or emitted is through the sun's solar plasma during solar flares, supernovae, the deadly explosion of a star after it loses its fusion and collapses, and through colliding black holes. And we can get black holes through supernovae, and I really want to go over the subject of black holes. I'm just saying that right now. I really want to go over black holes with you guys. And when we're done, when we're done with our particle physics, we will finish, and we'll get to our black holes, string theory, dark energy, dark matter. So thanks for watching the episode, and leave it a like and subscribe, and we will come back for the next episode. Thank you.